Alright, so the last thing to finish up in 6.1 is what we call arc length. And then we're also going to look at something called angular speed. Okay, basically the speed of something spinning. So we'll see how much we get to. Alright, so let's talk about arc length first. Okay, so the idea of arc length is you're figuring out how long part of like the perimeter of a circle is. Like the whole arc of a circle, that'd be a circumference. An arc usually refers to part of the circumference. Could be the whole thing, but usually it's just a small part. All right, so I want to draw a couple pictures and see if you notice a pattern. All right, so here's a circle. Here's an angle. And what's the size of the angle that I just drew?
90 degrees.
All right, so a 90-degree angle. And here's the arc that connects the terminal side and the initial side where the initial and terminal side hit the circle. How much of the circle does that arc take up?
A quarter.
Yeah, it takes up a quarter. So a 90-degree angle, you get a quarter circle for the arc. All right, let's draw another one. Okay, this time I'm going to draw this angle. And what's the size of that angle?
180 degrees.
So that's 180 degrees. And the arc for that is from here to there. How much of the circle does the arc take up this time? It takes up half. Okay, so now I want to look at what happened here. I started with 90 for the angle, and I went to 180. What happened to the size of the angle?
It doubled.
It doubled. It went from 90 to 180. Now, what happened to the size of the arc? It went from a quarter circle to a half circle.
Also doubled.
It also doubled. So what that means is any change in the size of the angle is directly related to a change in the size of the arc. If you triple the size of the angle, you triple the size of the arc. If you make the angle half as big, you make the arc half as big. They are what we call directly proportional. Okay? Changing one directly changes the other the same way. Any question on that idea? Arc size and angle size are directly connected. Okay. So because arc size and angle size are directly proportional, we can do a proportion, okay, to find a formula for the length of any arc. Now, the way we're going to figure out the formula is we have to start with something we know is true. I think I did an example like this yesterday when we, I think I may have used like feet and inches. What's a true fact between feet and inches?
12 inches is 1 foot.
It's 12 inches in 1 foot. So now if you want to know how many inches in 8.5 feet, I can just say there's this many inches in 8.5 feet. And now I have a proportion and I can cross multiply. Now, besides 12 inches in 1 foot, could I do 24 inches in 2 feet? Is that also true? Yeah. It doesn't matter what you put there, as long as it's something that's true. Preferably simple, but anything true will work. Well, that's what we have to figure out here. We've got to figure out a fact that we can start with that's true, any fact, between an arc and an angle. Okay, so we got to come up with something that's true. And we're going to use this diagram. If you're going to set up a proportion, you need four things. That's an S, and it represents the length of an arc. That's the letter that our book uses. Theta represents the angle that makes that arc. S1 is another arc, and theta 1 is the angle that makes that one. If we can figure out one of these, then we can automatically figure out the other one. It's kind of like if we can figure out one side, you can automatically figure out the other one. Okay, you just need to be able to figure out one side first. Okay, and I'm going to give you a hint, and it's going to tie in with what we did yesterday. Now, you don't have to suppose that it's 1 radian, just like you didn't have to tell me that 1 foot is 12 inches. You could have said 3 feet is 36. But if we use a 1, it's the simplest way to do it. If this angle from here to here is 1 radian, then something special happens to this arc. Does anybody remember from yesterday? If you have an angle of 1 radian, then this arc is the same length as something else automatically. Yeah?
The radius?
The radius. And that's the fact that we're going to use. So if your angle is 1 radian, then your arc is automatically equal to the radius. This is like your 1 foot 12 inches. It's a definition. It's a fact that's true that you can start with. Is it the only fact? No. But it's the easiest one. So if the angle is 1 radian, then the arc is equal to the radius of the circle. Definition. Okay, so now let's set up a proportion and see if we can plug that in and get a formula. Okay, I'm going to set up the left side. That's the side that we're going to fill something in on, and then the right side, that's going to be the stuff that we don't know. All right. So the stuff that we're going to fill in. Okay. Let's do theta 1 over S1. That's going to be the stuff that we fill in on the left. On the right, it's going to be what we don't know. How would I set up the right side? And it has to be set up with the same pattern I did on the left. Yep.
So it would just be theta over S?
Yep, theta over S. Now, fill in the side that you know. That's going to be my 1 foot 12 inches. Fill in the fact. So theta 1 is going to be a 1. And S1 is going to be R. Now the other side, we just leave it, because that would be information they would give you in the problem. Okay, theta over S. Right, so that proportion is pretty much exactly the same thing as that one. Except we also have a question mark right there as well. All right, now when you solve a proportion, does anyone remember how you do it?
Cross multiply.
You cross multiply. Okay, so what's S times 1? S. And how about R times theta?
R theta.
It's just R theta. And that's the formula for the arc length. It's S equals R theta. So S is the length of the arc that you're trying to find. Okay, R is the radius of the circle. And theta, that's a Greek letter. What do Greek letters usually represent in trig? Represent an angle. Now we got to be careful about the angle. Let's go back up and let's look at the fact that we started with. Let's look at that 1 foot 12 inch kind of fact. I have it circled in the upper right. What did we assume about our angle?
That it's 1 radian.
1 radian, okay? It's not important that we assumed it's a 1. Just like with 1 foot 12 inch, you could have done 2 feet 24. The number is not important, the unit is. You assume that the angle was in radians. So that means in this formula, it only works in radians. So if you get an angle that you need to work with in degrees, the very first thing you have to do, switch it to radians. Okay, and really the way that this works, they're going to give you 2 out of 3 of the letters. You fill them in, and you find the third one. That's it. Does everyone have the formula? So I'm just continuing. I think I left off with example 5 yesterday, so I just continued with 6. All right, so find the length of the arc. If you have a circle with a radius of 2, and the angle that's making the arc is pi over 4. So they can give you the problem as a sentence. They could also give it to you as a picture, or they could do both. So you are finding this part in red, right there. Okay, so first thing is just to write down our formula. What is the formula that we use to find the length of an arc? Yep. S equals r theta. And then I go through left to right and I fill everything in that they tell me in the problem. Okay, let's start with S. Do they tell me what S is going to be in the problem? No, they don't tell me that because that's what I'm finding, right? They tell me find the arc length. So I'm gonna leave S as S. But do they tell me anything? Like what about R? Do I know that?
It's 2 inches.
I know that that's 2 inches. All right. And do I know the theta?
Yep. Pi over 4.
That's pi over 4. If you want to think of the 2 as a fraction, you can. You just multiply straight across. So we're going to get 2 times pi over, that's pi, 1 times 4. But 2 pi over 4 reduces to what?
Pi over 2.
Pi over 2. Now we got to be careful because we need to put a label on that. What did we just solve for?
Radians. Or the arc length.
We solved for the arc length. So we solved for the length of that thing in red. So what kind of label do you think we should put on that? Inches. S is a length. So you always put the label that they use for length. R is also a length. The only thing in this problem that should have a label of radians is the angle. So pi over 2, well, that's 3.14 divided by 2. It's about 1.57 inches. If they ask for a decimal, you could do it. Otherwise, just leave it like that. Pi over 2 inches. Any question on that one? It's a pretty straightforward formula. So not much with it. Let's try one more. Okay, so this says find the radius of the circle if the arc length is 3 pi feet and the angle is 60 degrees. Okay, so first thing we should start off with is write down the formula. And then we know what we're plugging into. What's the formula that we are going to use to plug in all these numbers? Yep. S equals r theta. Now, before we start plugging in, does anybody notice anything in this problem we might have to do first? Something here that's not good for that formula. Yep.
So switch to S and R.
What do you mean switch the S and the R?
So we're solving for the radius and R.
Oh, it's like divide each side by theta? Yeah, so you could rewrite the formula if you wanted. So now you know the calculation you're going to do. It's going to end up being S divided by theta. Bless you. But I'm still not ready to use that formula. There's something here that if we don't fix, it's going to come out wrong. Yeah?
Is the angle? Oh, never mind.
Is that?
It has to be in radians.
The angle has to be in radians. You cannot plug in 60 degrees. Okay? So off to the side, it's part of the problem. It's not the final answer. We need to change this to radians. So 60 degrees. What do we multiply by to change to radians? Yep. Pi over 180. Yep. Degrees is going to cancel. And what does 60 pi over 180 reduce to?
1 pi over 3. So just pi over 3.
Yep. That's going to be 1 pi over 3. That's what you plug in for theta. All right. And I'm going to use the original formula because I'm going to guess some people might not thought to do that, to get the variable by itself first. You don't have to. So if you just said, I'm going to use the original formula, do they tell me S? Yeah, what is S? So it's 3 pi. Yep, feet. So we'll keep that in mind if we need to put a label on the answer that's length at the end, which we do. It needs to be feet. So 3 pi feet. Do they tell me the radius?
No.
No, that's the whole question. Find the radius. Times. And what's the angle that I fill in?
Pi over 3.
Pi over 3. Now, you could say, yes, you're going to divide both sides by pi over 3, but that's a fraction. Does anybody remember something you can multiply both sides by, and it'll get rid of the pi over 3?
Maybe 3? No. 3 pi.
Nope, not 3 pi.
3 over pi?
3 over pi. It's the same way you would solve something like 2/3 x equals 12. If you have a fraction next to a variable, you want to get rid of the top and the bottom, you multiply each side, does anyone remember the name of that? By the reciprocal. So in this case, 3 over 2. In this case, 3 over pi. So multiply by 3 over pi. 3 over pi. And when I do that, what cancels on the right? Pi's. Yep. And the 3's. Anything else that cancels in the problem? The pi's on the left also cancel. I'm not saying everything's going to always cancel on the left like that, but on the right it should, because that's why you use the reciprocal. Okay. So what do I get for a radius? 9 feet. So there's an example where you're using the arc length formula and you found the radius. So first one we did the arc length, that one we did the radius. Finding the angle would be the same way. You fill in the two things they give you, solve for the one you're missing. Okay, you have a few questions on the test like that. Any question on arc? Yep.
The angle representation follow the same degree rule? Like if it was theta degrees, it would be in degrees, and if it's just theta, it's always radian.
In this formula, theta is always radians. Yeah. So like if you had a problem where, if you were going to fill into that formula, and let's say S was 10, and let's say R was 5. If I were filling that in and solving for theta, it would be 10 equals 5 times theta. And when I divide each side by 5, I get 2 for theta. And that is not 2 degrees, that's 2 radians. Now, if they asked you for the answer in degrees, you could take that and change it by multiplying by pi, or multiplying by 180 and dividing by pi. Okay, but when you use the formula, that is radians. And I should ask this too. Do I need a label on the 2? No, I don't put a label because it's radians. And you won't see a label on the homework or on the test. But degrees, you do need to put a label. So if you need to put it in edge elastic, we haven't used the degree symbol, but when you click in the box, it'll pop up for you. It'll be like an X. Yeah, you'll see it. Okay. Any other questions on our? Okay. All right. So now we'll look at the last thing here today. Okay, so arc length, that was the first thing. Angular velocity is the second. Angular velocity, or you could also say angular speed. It just measures the speed of something spinning, rotating. Could be rotating in place, kind of like a drill bit rotates in place, or it can be something, rotating around the perimeter of a circle. Anything spinning, any kind of spinning. And there are really 3 units that we can use to measure something spinning on a circle. We can measure how many degrees it moves on the circle. We can measure how many radians it moves. Or we can measure how many revolutions. All 3 of those things I just said measure distance on a circle, movement. When we talk about something moving on a circle, we wouldn't use something like miles or feet. We always stick with one of those 3, degrees, radians, or revolutions. You've probably seen revolutions, like if you see RPMs, revolutions per minute. That's measuring something spinning. We generally wouldn't use RPMs to describe like something moving in a straight line, like on the road. Right? If you get pulled over, you don't get pulled over for going 5,000 RPMs. That's not how it works. So RPMs is something spinning. So why do we need that? We already have a way to measure speed that's in a straight line, like miles per hour. Why do we need revolutions per minute? Okay, that's what I'm going to show you. Yeah.
I was just going to ask if this was where 3.82 came from.
3.82?
Yeah, it's a simplification. I don't know if this simplifies down to that.
What's 3.82?
When you're calculating for like RPMs for like an end mill or whatever, we use 3.82 to simplify for pi to determine like the speed of the end mill that has to go.
Oh. So that might
part
be
of the formula. I thought it came from this.
So yeah, that might have something to do like with a shortcut, some type of conversion to change something to something.
Usually we use 4, but 3.82 is the technical term.
Yeah, I'd have to see what you're doing, like converting from and to. But yeah, it might have to do with this.
Yeah, constant surface foot per minute, depending on the diameter of the cutter.
Yeah, so yeah, it could have something to do with this. Yeah. So when we talk about speed of something moving in a straight line, does anyone remember the distance formula? It's distance equals, and then it's usually 2 letters multiplied together. Rate times time. Distance equals rate times time. So let's look at this wheel. Okay, there's three different dots on it. Kind of that black dot in the center, then the red dot, and then the black dot on the outside. So I'm going to take and make 1 revolution. I just want you to watch the dots. And as I go around 1 time, does everyone agree they all made 1 revolution? Okay. Were all the revolutions of each dot the same size? No. Which dot made the largest revolution? Yeah, this dot. Oops. This dot made the largest revolution. So this dot traveled the furthest, but it traveled the furthest in the same amount of time as all the other dots. So if this one traveled further in the same amount of time, what does that mean about the speed of this dot compared to the speed of that dot? Right, this dot would have to be going faster. And that's what gets confusing if you try to describe the speed of something spinning in a linear way. Every single point on the surface of that circle is going at a different speed relative to the center. In fact, you might say the center has a speed of 0 because it doesn't move at all. So the distance of the center dot is 0. Well, distance is 0, that means it didn't go anywhere, so it doesn't have any speed. The simpler way to describe the speed is just to say all of these dots made one revolution in, say, it took me 2 seconds to do that. So they all have a speed of 1 revolution in 2 seconds. So that's the same. What's different is the size of the revolution. Okay. Any question on that idea? So that's angular speed. So the unit that we generally use for angular speed, and this is where the book, they don't do a good job wording the question sometimes, because they'll just say, find the angular speed. Well, if they don't tell you a unit to use, I always want you to stick with radians. The time unit, I don't really care about. Use whatever time unit is in the problem. If it's minutes, we'll do radians per minute. If it's seconds, we'll do radians per second. And if they want a unit other than radians, then they need to tell you that in the problem. Like if they want revolutions, they need to say in the problem, find the angular speed in revolutions per minute, per second, whatever the time is. If you don't see a time, stick with radians. Now, if you compare that to linear speed, those are the units that we're more used to using. Miles per hour, okay, kilometers per hour, feet per second. So linear speed, that doesn't measure the speed of something spinning. It measures the speed of something moving in a straight line. Now, there are 3-letter abbreviations for some of these. In general, I would stick to writing it distance / time. That's how I would do it. The only time you might see a 3-letter abbreviation is revolutions per minute. You might see RPM. Miles per hour, you could see MPH. And then kilometers per hour, you could see KPH. But other than that, like I would never write FPS for feet per second, because in computers, FPS could be frames per second. So a lot of times the 3-letter abbreviation may be confusing, what the letters stand for. But I think most people, RPM and MPH, I think most people are familiar with those. Any question on that? Okay. So the way that we're going to convert the things we're going to do is we're going to look basically like we do at radians and degrees. Look at the dimensions. And we're going to say, okay, we got minutes in the top. We're trying to get minutes to cancel. Where does it go? It goes in the bottom of the other fraction. So we're gonna look at our units and analyze the dimensions to make things cancel. Now, to do that, there are some conversion factors that I would expect you to know. Okay, I'll tell you the ones that you need to know. And if there are any that we're unsure of, you can ask me right now. So how many seconds in a minute, minutes in an hour, hours in a day, days in a typical year, how many inches in a foot, how many feet in a mile, how many feet in a yard. I'd say that would cover most of them. Okay, any of those conversions that people aren't sure about?
Feet in a mile.
Feet in a mile. 5,280. Yep. 5,280 feet in 1 mile. Any other conversions there that people aren't sure of?
Feet in a yard.
Feet in a yard?
Yeah.
3. 3 feet in a yard.
I never use yards. I would
Yeah.
never use that in my life.
You wouldn't have to know a conversion like how many millimeters in a mile. I mean, that's kind of a weird conversion. Most people don't know that. So something like that I would help you with, but those conversions you need to know. All right, so let's try some examples. Now, the first one isn't even a velocity. This is not velocity. This is just time. 3 days. Okay, so we're going to convert 3 days into minutes. It helps to have everything as a fraction. So to make 3 a fraction, what could I put in the bottom? Yep, put a 1. And we're going to go 1 unit at a time. So we're going to go from days down to the next smallest unit. What's the next unit that we use below a day? Hours. So I need a conversion that has days and hours in it. Now I have days in the top. I'm trying to get rid of days and eventually get to minutes. Where would days go to cancel out? Days would go in the bottom, and hours would go in the top. What's the connection between days and hours?
It's 24 hours in one day.
24 hours in one. Yeah, it's not supposed to be plural. That's fine. In one day. Okay, so now days is gone. And if you stop there, you have hours. Okay, now we'll go to the next unit. What's the next unit down from hours? Minutes. We're going to try to get rid of hours, so we end up with minutes. Hours is in the top. Where would hours go to cancel out? Bottom. So hours in the bottom. Minutes in the top. And what's the connection between hours and minutes? 60 minutes in 1 hour. So hours is gone. And what's the only unit we're left with? Minutes. Now you multiply straight across. In this case, all the denominators are ones. That doesn't always happen. So we just need 3 times 24 times 60. So 3 times 24 times 60. So it's 4,320 minutes. Any question on that one? So that problem had a single unit on the final answer. Just a time unit, okay, minutes. Okay, the next problem, the next problem is going to have 2 parts to the final answer. It's going to have a distance part, and it's going to have a time part. When you have a distance and a time part on your label, that's a speed. That's a rate. So we're going to convert 50 feet per second into miles per hour. So 2 things need to be fixed. Feet has to change to miles, and seconds has to change to hours. So when they say this, what does that mean? 50 feet in how much time? 1 second. So you're traveling 50 feet per 1 second. Now it doesn't matter which unit you fix first. We can convert the distance or the time first. Which one do you want to try first? Time. Okay, so the first thing we're going to do is we're trying to get seconds to hours. What's the unit we're going to go through in the middle? Minutes. Where would seconds go? It's in the bottom here. If we want it to cancel out over here, it's going to go in the top. So seconds in the top, minutes in the bottom. Connection between minutes and seconds?
60 to 1.
Yep, 60 to 1. 60 seconds in 1 minute. Okay, what unit is gone now? Seconds. Now, if that's all you did, you'd have feet per minute. Okay, now let's keep going and get minutes to hours. Okay, so this is when you say dimensional analysis, that's what we're doing. We're looking at the dimensions and figuring out where they need to go. Where does minutes need to go? In the top. And what's going to go in the bottom? Hours. Okay, connection between minutes and hours. 60 minutes and 1 hour. So now we got minutes. Now we have feet per hour. So now we got the time unit where we want it. Now we get the distance unit. So the next conversion is going to involve feet and miles. Even if you don't remember how many feet in a mile, you should know where feet is going to go. We're trying to get rid of it. So feet has to go in the bottom, miles in the top. Now you need the numbers. What's the connection between feet and a mile?
5,280 to
5,280 feet in 1 mile. feet in the bottom, feet in the top. Okay. What unit am I left with in the top? Miles. And what unit am I left with in the bottom? Hours. So multiply it out, and that's our answer.
34.1.
What is it?
34.1.
34.1. Okay. So you just 50 times 60 times 60 divided by 5,280. Okay, so that was our first one, converting a rate. Now, what kind of rate is that? Is that a linear speed or an angular speed?
Linear.
That's linear. Feet measures straight line. How about miles per hour? That's also linear. So we did a linear to a linear. Okay, the next one we're going to do is angular to angular. So we're going to convert 200 radians per second to revolutions per minute. Now, these conversions might be less familiar because we just started learning them yesterday, but it's exactly the same steps that we did up above. 200 radians per second. Is there any part of my label this time that I don't need to fix, or do I need to fix both parts? Yeah, I have to fix both. I got to get radians to revolutions, and I got to get seconds to minutes. Well, let's do the seconds to minutes. Okay, hopefully by now you're kind of getting the hang of the minutes to seconds and that stuff. Now we got to get radians to revolutions. Okay, even if you don't remember what the number is, you're trying to get rid of radians. So where would radians go?
The bottom.
Yeah, it's going to go in the opposite spot. So radians in the bottom, revolutions in the top. Now, what's the connection between radians and revolutions?
2 pi radians.
Yep, there are 2 pi radians in one revolution. There you go. So I'm going to put approximately because we're going to use pi, so it's not exact. The way I would type it in is 200 times 60. So the calculator knows do the top first. And then divide by. It'll do 2 times pi, and then divide the top by what it gets. Okay, so it's 1,909.86. Wait, 1,909.86. And what's my label on that?
Revolutions per minute.
Yep, that's revolutions per minute. So that's one way sometimes you do see RPMs. Okay, so that was angular to angular. Any question on that? All right, so the last one is angular to linear. So the idea of what's happening here is you've got a wheel that's spinning maybe on a machine at 1,850 revolutions per minute. So the idea is that if that wheel were to come off the machine and hit the ground, and it didn't lose any energy or any traction, if it hit the ground, all of a sudden that wheel is going to take off in a straight line. We're going to figure out how fast it would be going if all that spinning was converted into moving in a straight line. That's what we're going to figure out. So we're going to need everything they give us to do that. You're going to need the 18 inches and the 1,850 RPMs. All right, let's see what we can do. I'm not going to do A. I'm going to skip A. Because A is just converting RPMs to radians per second. Well, we just converted radians per second to RPM. It's the same thing we just did. It's just in the other order. So is there any question on 7C? Where you want to see like revolutions per minute to radians per second the other way? It's pretty much the same thing. Okay, I want to look at part B. Okay, that's the part that's different. I'm going to do that. So I want to find the linear speed of a point on the circumference of the wheel. So like I said, if the wheel were to hit the ground, fall off the machine, how fast would it start rolling? Right on the edge of the wheel. So anytime that they give you a problem where they want you to go from an angular speed, like revolutions per minute, to a linear speed, you have to go through revolutions. That's how you do it. So if your angular speed is not in revolutions, that would be your first step. That's already in revolutions. Okay, so we're going to use that. So RPM, that's revolutions per minute. 1,850 revolutions in a minute. Okay, mine has minutes. What's the time unit they want in the final answer? Okay, so we got to get it to seconds. So let's fix that. What would I multiply by to change minutes to seconds? 60. So 60.
No, 1 minute.
So 1 minute, there's 60 seconds. So you're actually dividing by 60. So question on fixing the time. Okay, now, we want to convert revolutions to what unit for the final answer? Feet. Okay, we're going to have to figure that out. But before we even figure out the number, where does revolutions go? It goes in the bottom, and feet goes in the top. Now, put a box around that conversion because this conversion is something you have to figure out every time you do this. It's not like how many seconds in a minute, how many feet in a mile. It's not a conversion that's the same. How many feet in a revolution? Well, it depends on how big of a revolution. Is it a small revolution? Or is it a big revolution? Now, if you think of a revolution as a circle, a revolution is really the what of the circle? It's the circumference. So what we have to find is how many feet in the circumference of the circle. That's one revolution. So what's the formula that we use to find circumference? What is it? 2 pi r. Yep. So circumference is 2 pi r. What's the length they want in the final answer again? What's the unit? Feet. Okay. What do they tell me that my radius is?
18 inches.
18 inches. What would 18 inches be in feet? 1.5. Yep. It's exactly 1.5 feet. So I want to use the 1.5. I don't want to use the 18. If I couldn't figure it out, just divide 18 by 12. That's how you get inches to feet. Okay, so 1.5 is my radius. So the circumference is 2 pi times 1.5. What do you get when you simplify that, but you can leave your answer with pi? No decimal. 3 pi what? For the circumference? So the circumference wouldn't be in radians because that's a distance around the circle. Feet. So what does that tell me? This tells me that there's what?
A rev and a half.
Yeah.
There's 3 pi feet in 1 revolution.
There are 3 pi feet in 1 revolution. Yep. That's the circumference of the circle. So now we know that there are 3 pi feet in 1 revolution. And again, that conversion will change for every problem you do. Depends on the size circle. Alright, so now revolutions is gone. And we're just going to multiply 1850 times 3 pi. Times 3 pi. I only did times pi, so times 3. And what do I need to divide by? 60. So that's a speed of 290.6 feet per second. Okay, so what do you think? Is that fast speed, a slow speed?
That's slow. Pretty slow.
Pretty slow? All right. So that was 290 feet per second. So we did,
It's moving.
what did we do earlier? Okay, we did this one. We did 50 feet per second, and that was about 34 miles per hour. Okay, this is 290 feet per second. So that's almost 6 times as fast. If it was 300, it would be 6 times. So if you multiply that number by 6, it's about 200 miles an hour. The slow? Yeah, that's not slow. Yeah, it's slow. I mean, relative, I guess, but it's 200 miles an hour. So the point is, if you were standing anywhere probably inside and the tire came off at 200 miles an hour, you're probably not getting out of the way. Even if it was a football field away, 200 miles an hour coming at you, it's still pretty fast. We wouldn't have much time to get out of the way. Less than a second. All right. So any question on the conversions between angular and linear? All right. So I think that's a good place. We'll stop with that. Okay. So for tonight, the homework is just the page 324.
Wait, is that just?
How long are these?
We're going to do 335 tomorrow.
Oh.
That's going to be part of tomorrow. Yeah, it's just that's a good place to kind of stop.
Yeah, but it's gonna be a really long problem.
No, I don't think so. But that's